All right, let's picture this. We've got our beautiful circle with a chord, a point somewhere on the arc, and from that point, two lines, one to each end of the chord, forming an angle inside the circle. Now add one more element, a tangent, to the circle, right at one end point of the chord. That forms another angle opposite to the first angle. And here's the thing, those two angles, by the mystical laws of circle geometry, they're declared to be always equal. Well, that's the alternate segment theorem. You've probably seen it before. It's one of those things you might memorize, maybe even prove in class. But have you ever stopped to ask, why? Not in the prove this with triangle congruence kind of way, but really, why should this be true? Let's decode this theorem together. First, notice something already remarkable about this shape. If you pick any point on the arc, the angle subtended by its corresponding chord stays exactly the same in that segment. It doesn't matter where the point is. Left side, right side, high up, low down. As long as it's in that segment, the angle doesn't change. And since we don't assume here, we'll schedule that proof for some other time. So that angle? It's constant. Now, what happens if we start to move that point? Imagine dragging it slowly. Let it drift. Down, closer and closer. Approaching the point where the chord meets the tangent. We're going to ride that angle all the way to the edge, and here's where things get interesting. As the point slides infinitely closer to the chord's endpoint, the adjacent side of the triangle tends to become the tangent itself. But even as the shape distorts, the measure of that angle doesn't budge. It's holding on. So that constant angle and the tangent angle behave like two angles formed on a straight line by two parallel lines. But now, push the point even further, all the way to its limit. Well, this is where we slip into calculus mode, but not the kind with heavy notation and formulas. Just the idea. We're talking about a limit. As the point touches the endpoint, that constant angle tends to be projected backward from the current segment, sitting comfortably on the opposite angle created by the tangent. See? This is what we mean by saying those two angles are equal. That's literally the alternate segment theorem, not as a memorized fact, but as something that must be true, because it's the natural outcome of the geometry we've built. Now here's the beautiful twist. This whole journey was hiding in plain sight. Every time we drew that constant angle, every time we saw it remain unchanged along the arc, we were tracing out a hidden limit, a destination. So the moment we step off the arc and land on the tangent, we're not breaking the rule. We're revealing the end point of a rule that was always there. This is what makes geometry feel alive. And hey, if that made perfect sense, wonderful. If it didn't, no problem. Go back, re-watch, let the pieces click. Math has a funny way of working like that. Sometimes, it reveals itself slowly. So, until next time, keep your angles constant, your limits sharp, and your curiosity endless.